This is the first day of MCA practice and review. And again, it's one of those things where, yes, the juniors take it this year, but everybody can benefit from it because a lot of the topics that are going to be on the MCAs are things that are also going to show up on the ACTs. And at some point, everybody's going to have to take the ACTs if you want to go to college. So let's take a look at the topics we're going to talk about for the practice for day one. We've got stem and leaf plots, sample size, correlation versus causation, probability, and expected value. So these are all things that you would have taken in the Prob and Stats class that you had second semester of the year that you took exponential algebra. And that means for some of you, you've never seen this before, especially if you were one of the people that was accelerated into Algebra 2. That was one of the ways that they got you through, was by skipping that Prob and Stats class. So you need to see some of these. Example 1 says we're going to make a stem and leaf plot of the following data. And on the MCAs, they won't have you make the stem and leaf plot, or they might have you do that as background for something that they're going to ask you. So you need to be able to make the stem and leaf plot so that you can answer the questions. Because again, this is all going to be scored by a computer. It'll probably be in a multiple choice type of format based on the fact that you are supposed to be able to draw a stem and leaf plot. And that's how I'm going to treat every one of these. I'm going to give you the background math to get there, knowing that it might be kind of a fill in the blank or grid problem, or it might be multiple choice. So example 1, we're making a stem and leaf plot of the following data. And what a stem and leaf plot does is it organizes the data with what are called stems, and those are the numbers that we're going to put in the front here of this vertical line, and then leaves. So we've got the singular there, which is a leaf. And what you want to make sure you do is that you separate these numbers in a way so that we have one number in each of the leaf positions. Well, because this is just tens, that would mean that all of the tens digits will go in the stems. So we have 11, 12, 14, 15, all of those have a 1 in their tens digit. And then we have numbers in the 20s and numbers in the 30s. And now you go back and you find all of the numbers that have a 1 in the tens position, and you put them in order, but you don't use the 1. The 1 is already taken care of by the stem. So I have an 11, a 12, a 13, a 14, and a 15. This takes care of the 11, the 12, the 13, the 14, and the 15. And while I'm writing this down, hopefully you're thinking, okay, well then you're going to need a key to tell somebody that that's what that is. And that's what you do with a stem and leaf plot. You make a key. And you just pick something. It doesn't have to be on your stem and leaf plot, but for instance, let me take 1 and then the vertical line and 3 and use an arrow to show people that that means a 13. So there's our key. But again, what it does is it orders the information, the data that you have, in case they should ask you for the median. And remember, everything has to be in order for you to talk about where the middle one is. And it just organizes your data really nicely. So now we're done with anything that had a 1 in those tens position. And let's go back and look for anything that has a 2. So we have a 21, 23, 23, and 26. So we've got 21, 3, 3, 6. And again, our key would show somebody that that represents the 21, 23, 23, and 26. And then we go back and grab anything from the 20s, and notice I'm using a strike here so that I can still see that data, but I know I've used it already. So for the 3s, for 30s, we have 33, 34, 35, and 36. 3, 4, 5, 6, 33, 34, 35, and 36. Now, this could be used for them to ask you, median could be used to ask you for mode. Median is the middle one, and if that's the case, you'd count them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. and you'd figure out that half of 13 is 6.5. So that's actually the number that's in the 7th position. That would be our median. So 1, 2, 3, 4, 5, 6, 7, and that 3 is represented by 23. So the median would be 23. And the mode, remember, is the one that's there the most. And when you relook at this data, you see, oh, well, that's going to be 23 also, because that's the only one that we had 2 of the exact same number in there. So median and mode can definitely be found a little bit easier with stem and leaf plots. So example 2 down here, I want you to go ahead and pause the video and make a stem and leaf plot for that one on your own. All right, just giving you that so you have a chance to check it. Again, they'll probably ask you some questions about your stem and leaf plot and what you have. Now, you could also see a back-to-back stem and leaf plot. And so the best way to learn how these work is to just make one, because then you can get a feel for how all of the data works. So we're going to make a back-to-back stem and leaf plot for the following data. And we have a set of data about boys and another set of data about girls. And with this, what we want to do again is put something, and this time it's going to be between our 2 vertical lines, so that every number that we use to represent the leaves, which would be out to the sides, that is just going to be 1 digit. Well, again, fortunately, I made all of these, so these are 10s, and we can see that we're going to have 10s, 20s, 30s, 40s, and if you look real closely in the boys, you see we have one in the 50s up there. So now what we have to do is represent both the boys and the girls, but what we're going to do is we're going to keep all of the boys' information over here on the left and all of the girls' information over here on the right, so that they're separate, but you could still find them really easily. And what you have to do when you make a back-to-back stem and leaf plot is work from inside out. Now the girls is going to be like normal, and just to save some time here, I'm going to tell you that I went ahead and made the girls already. 2, 2, 3, 4, 5, 7, 8, and 3, 3, 4, 4, 4, 5. So this is just like the normal stem and leaf plot for the girls. But for the boys, we'd have to work backwards. So we'd look for anything that had a 1 in the tens digit, and we don't see any. But then we go to the 2s. And so we see 21, 22, 22, 22, 23, and 23. But we have to write these backwards because we want them in order from the center. So there's our 21, 22, 22, whoops, sorry, got to put it down here by the 20s. 21, 22, 22, 22, 23, and 23. So from the inside out, back-to-back stem and leaf plots. And then you'd go through the 3s and see anything in the 30s, and that's going to be 4, 5, 6, and 7. And anything for the 40s, 3, 3, 4, 5. And for the 50s, we have a 51 for the boys. And then you have to make a key, and you have to represent everything that you would possibly see up here. So a good choice would be something using the 20s or the 30s. I'll go ahead and pick from the 30s, and I'll just do 34 and 33. But we need 2 arrows to let people know that as you read this to the left, that's 34, and as you read this to the right, that would be 33. So like I said, this is a back-to-back stem and leaf plot. They might give you one of those. Again, ask you median mode. In fact, they might even ask you to find the mean, the average, adding them all up and dividing by the number that you have. Any of those things would be easy to do once you have everything organized in the stem and leaf plot. So we have to remember what those are. Next up, sample size. The sample size is the number of pieces of data that you collect. The more data you collect, the better your sample is going to be. And you can use that to make predictions about what's going to happen in the future. So the next line here says the larger the sample size, the more reliable the results. That is absolutely true. The bigger your sample, the better you can use the information. You can use it to make predictions. So example 5 says, Doug attends a school with a population of 4,554 students. Doug is always trying some kind of get-rich-quick scheme. Doug decides that he wants to try to sell his mother's pickled beets right before lunchtime each day. He asks his 4 closest friends what they think of the idea, and they tell him they think it's a great idea because they all love his mom's pickled beets. Doug decides to try to sell the pickled beets. Is Doug's reasoning sound? Why or why not? Well, of course it's not. No, it's not. He's got his opinion, and he has the opinion of 4 of his friends. That's only 5 people that like pickled beets. I mean, if he asks anybody else in the school, they might say, I wouldn't even put a pickled beet in my mouth. So this is a no. His reasoning is not sound because his sample size is too small. Now, other reasons that you could think of, maybe they just don't want to hurt his feelings. They don't want him to go back and tell his mom, all my friends hate your pickled beets. They've been choking them down for years, so they're not really telling the truth when he asks them. It needs to be a larger sample. It needs to be random people, all of the wonderful things that you learned about in problem statistics. Now, 2 major topics in probability and statistics. Correlation. Correlation is when 2 pieces of data have been shown to have a mathematical relationship. Now, that can happen in all kinds of situations where there's actually some kind of strange mathematical connection between 2 pieces of data. It does not mean causation. Causation is key. So causation says when 2 pieces of data have been shown to have a mathematical relationship in which one appears to cause the other. So this would be an instance where I think about things that come from the pharmacy. You give the medication and the desired effect occurs, the relief of symptoms occurs. That's causation, when you actually see one is making the other happen. Unfortunately, there are a lot of situations where, yes, there is a mathematical correlation, but no, they don't cause each other. So in example 6 here, we want to know, is this correlation or causation? And we have women's skirt lengths and the stock market. There is absolutely data that says these 2 things are mathematically linked. When the stock market is doing well and things are looking on the upside for the economy, women's skirt lengths go up. They get shorter and shorter. And there has been a mathematical relationship that's shown. There's studies about that. Now, does that mean one causes the other? No. It just happens. If the economy is good, people have more disposable income. And if they have more disposable income, well, then there's more time for them to shop with all the latest fashions. And maybe that's when miniskirts suddenly became the in thing. So they don't cause each other. That's just a mathematical correlation, a strange mathematical relationship. Benadryl, otherwise known as the generic diphenhydramine, and the relief of allergy symptoms. Well, that's what it's for. That's the reason that they sell it, is for the relief of allergy symptoms. You take the medication and your allergy symptoms are relieved, hopefully totally, but maybe you get a little bit of feeling better off of that. So this is definitely causation. They wouldn't allow, the FDA would not allow the Food and Drug Administration, the medication, to be used for the relief of allergy symptoms if it wasn't proven that it actually did that. The next one that we see here, ice cream sales in the U.S. and shark attacks. This is also has been proven that there is a link between the two. When we eat more ice cream in the United States, there is an increase in shark attacks. Does that mean one causes the other? No, no. Again, this is correlation. You could try to logically reason that when the economy is good, people are eating more ice cream. And when you're eating more ice cream and the economy is good, you're going on more vacations, more people are in the ocean, and that's why they get bit, and you have the shark attacks. But definitely one does not cause the other. You don't go to the beach, get an ice cream cone, and go into the ocean and automatically get attacked by a shark. That doesn't make any sense. So it's a weird math relationship, and it happens. Gasoline prices and the speculators market. A lot of times we hear about how gasoline prices are hooked with supply and demand. And yes, that is a part of it. But overwhelmingly, the bulk of our gasoline prices are created by the speculators market. And it's a group of very wealthy people that sit around and try to foretell the future. If they think there's going to be a war in a region where we are using the oil that they ship us a lot, well, then the prices are going to go up. And if that war doesn't happen, well, then they'll let the prices go back down. But these two things, this is actually causation. Like I said, we like to listen to the news, which occasionally we'll hear about supply and demand. Yes, that is true to some extent. Usually in Minnesota, we'll see the price of gas go up in the summer, and that's because the weather is nice and more people are going to be traveling. And so yes, we're going to use more gasoline. So that part is supply and demand. But truly, the causation of gasoline prices going up or down is thanks to the speculators market. Next piece that we have here just starts talking about probability. And jelly beans and drawers with socks in them seem to be a real hit when you're talking about probability on standardized tests. So there is a jar of jelly beans on the shelf. It contains 12 red jelly beans, 16 purple jelly beans, 15 yellow jelly beans, and 17 green jelly beans. What is the probability that you will reach in without looking and choose a purple jelly bean? So what we need to figure out is how many purples are there out of how many total, because that's how probability works. So we look up there and we see that we had 16 purples. And we could grab a calculator and we could add up 12 plus 16 plus 15 plus 17. I'm just going to tell you that comes out to 60. And we could reduce both of these by dividing by 4. So you might see the probability in fractions. You might see it as decimals. You also might see it, since it's probably a multiple choice problem, as a percentage. So 0.267 is what we would get as a decimal. And then we'd look down at the answers and, oh, look, they're all in percentages. So then we would move the decimal over 2 places and say 26.7%. Now, B says, what is the probability that you'll reach in without looking, pull out a green jelly bean, eat it, and then reach in and pull out a red jelly bean? Well, let's start by talking about what's going to happen with that green jelly bean. So we want the number of green jelly beans out of the total. And there were 17 green jelly beans out of 60. Now, that's going to happen, but the next thing that's going to happen is you're going to eat it, so you can't put it back in. So that means now there are only 59 jelly beans left in there. And whenever you want two things to happen at once with probability, overwhelmingly the way that you get that is by multiplying. We learned pretty early on in probability that if we're talking about the word and, so we want green jelly bean and red jelly bean, that means we have to multiply these two pieces together. So now that I only have 59, I go back up and I look for how many reds there were. There were 12 red jelly beans. And again, you might see it as as a fraction, but it's more likely, I was going to say there's a higher probability, that they would have this one as a decimal. So 0.0576, and if you look down at your multiple choice answers, you might see that as percentage, so about 5.8% to the nearest tenth. You never know what they're going to ask you to round to, so you just be very careful following your rounding rules as you do that. So like I said, they like probability problems that involve jelly beans and socks for some reason. Alrighty, example 8. Using the figure below, find the probability that if you are equally likely to hit anywhere on the target, you will hit the outermost ring of the target. So right here. Now you're going to notice that kind of looks like a donut. And if it looks like a donut, donuts have holes in the middle. So if we want to figure out the area, which is what this is based on, this would totally be about area because it's a two-dimensional dartboard that we're talking about here. And we'd have to figure out how do you find the area of all this good stuff. And hopefully the first thing you do is say, well, I need the area of a circle. So what I'm going to have to do is I'm going to have to find the area of the great big circle and subtract the middle circle so that all I'm left with is that red ring. So let's take a look at how we could do that. Well, the big one on the outside has radius of 2 plus 2 plus 2, which is 6. So the big area is going to be pi times 6 squared, which is 36 pi. And I'm going to put area sub big. Now I want to figure out the area of the medium-sized circle that's inside that one. So I'm going to put area of median. Well, that one has a radius of 2 plus 2, which is 4. So that'll be pi times 4 squared, which is 16 pi. So now what I know is it's 36 pi minus 16 pi for the area of the donut shape that I have. And that's the area I need, and I need it to be divided by the area of the entire board. And the entire board happens to be a square that's 20 by 20. So the area of the board is 400. So hopefully you'd say, well, 36 minus 16, that's going to be 20 pi divided by 400. And we do have a pi button on our calculators, or you could just use 3.14. In fact, sometimes they'll actually give you that. They'll say use 3.14 for pi. But you would just punch this in and take 20 times pi and divide it by 400, and this is approximately 15.7%. Example 9, using the figure below, find the probability, if you are equally likely to hit anywhere on the target, that you will land on the outside border. So this one changes it up a bit, because now what we're looking at is this border around the outside. And remember, nothing's to scale on any of these drawings by any stretch of the imagination. So I realize, well, I'm going to need the area of the square, so that'll be area square 28 times 28, and the area of that square comes out to 784. But what I'm going to have to do to figure out the area of that outside border is take the square minus the area of the big circle. So I'm going to have 784 minus the area of the big circle. Well, that's going to be pi r squared. And we have 3 plus 3 plus 3 plus 3, or 3 times 4, which is 12. So pi times 12 squared, or 784 minus 144 pi. And again, I have to divide that by the total, the whole board. And the whole board was the 28 by 28, which was 784. So with this one, you'd probably want to put some parentheses around your numerator there and just punch in 784 minus 144 pi, parentheses, divided by 784. And this comes out to about 42.3% that you would hit that outside border. So that's another set of problems that they really, really like on standardized testing, dartboard problems. Expected value. So been a while since you've seen this as well. And this is a weighted system to find the number that should be expected. So you can think of this kind of like your grades in this class where we have tests count for 80% of your grade and homework and quizzes count for 20%. So this says, for example, you've scored an 85 on your first test, a 78 on your first quiz, and a 100 on your homework. Tests account for 70% of your grade, quizzes account for 10% of your grade, and homework accounts for 20% of your grade. What is your overall grade? So all you do is you take your score and you multiply it by the percentage that it's weighted. So the 85, if you look up there, you're going to see that was a test. And it said 70% of your grade comes from tests. So that's why 0.70. We've been talking about this recently as we've been working on exponential growth and decay, that when we want to put things that have percentages in them into a math equation, we have to change it to a decimal. And then your 78 was your first quiz. And so you look down here and you see quizzes account for 10% of your grade, so 0.10. And then you had 100% on your homework, which accounted for 20% of your grade. And now we have your whole grade because 70 plus 10 plus 20 is 100% of your grade. And if you multiply those together and add, you're at 87.3. So you use those percentages to weigh what you have for each of your test, quiz, and homework scores. And then you're set. So you could see expected value. So example 10 says, well, let's do something with this. Find the expected value of the ticket sales below. So we have the ticket prices and we have the available tickets. But if I'm going to be able to figure out the expected value, I have to know what percentage of the tickets each one of these is. So the first thing we'd want to do is add all of these up. And if we add them up, I'm just going to let you know there are 90 total tickets. So if I'm going to find the expected value, for instance, I've got the $6 ticket, I'm going to need to know what percentage of the tickets were $6 tickets. Well, there were 30 of them out of 90. And that's going to be a decimal, which we could change into a percentage. So we'll just leave that. And then we go to the $8 tickets, and 25 of those out of the 90 were $8. $12 tickets, 25 out of the 90 met that criteria. $20 tickets, 10 out of the 90 meet that criteria. And so what we would do, and we could certainly reduce those first before we punched them in, but we wouldn't have to. We could just punch it in exactly as is with the ticket price and the probability, the percentage that we'd have that ticket drawn. And in the end, this will come out to $9.78. So I hope right now you're grabbing your calculators and you're punching things in along with this so that you can see how all of these percentages come from. I'm just trying to keep the video itself down time-wise so that when you watch it, you won't feel like, half your day is gone. Example 11, we've got find the expected value of the ticket sales below. I'm going to push this up, and then I want you to pause the video, and I want you to give this one a try. Find the expected value for these tickets. So hopefully you had the answer $8.60 for the expected value of the ticket sales below. And next up, we're talking about some nice table probabilities. It says use the table to find the probability that a randomly chosen person from the school would be a freshman or a female. Now, here is the key word in this problem. probability that they are a freshman or a female. Because if you look at this table, you're going to see there are some freshmen that are also females. That happens. So what we're really looking for when we're saying the probability that you're a freshman or a female is going to be the probability that they're a freshman plus the probability that they're a female, but we have to subtract those females that are also freshmen. Freshmen and female. Otherwise, we're double counting those folks. So we need the probability that they're a freshman plus the probability that they're a female, but we have to subtract anybody that's been double counted. So first things first, if you add up all the females, you're going to get a total of 1,063. And if you add up all the males, you'll get 1,086. So together, when we add those, we get 2,149. So out of 2,149, we want the probability that they're going to be a freshman. So we'd add up 234 plus 220, and that would give us 454. Probability that they're female. Well, still the same total of 2149. But the probability that they're a female is now adding everything in this row. And that's our 1,063. And now we have to subtract our double counted out of 2,149. And our double counted are the freshmen who are females, 234. And if you use parentheses on these, because our calculator loves it when we do that, you could go ahead and actually find the fraction, which would be 1,283 over 2,149. But it's very likely that you would see this one as a percentage, where they would say, what are the percentage of people attending this school that are both freshmen or female? And that comes out to 59.7%. So probability sometimes is just about, adding up a bunch of numbers to find a total and then looking at the individual pieces. And like I said earlier, when you have and situations, overwhelmingly, you're just going to multiply. But when you have or situations, you have to add and subtract anything that's going to be double counted. So example 13 says, let's keep using that chart up there, that table. And it says, using that high school data from above, find the probability that a randomly chosen student is a sophomore or a male. I want you to pause the video and try this one on your own. For this one, if we want the probability that they're a sophomore or a male, we have to figure out the probability that they're a sophomore, add that to the probability that they're a male, and then subtract anybody that was counted twice, which would have been the sophomores who are males. So again, there's addition that takes place here as you add up the column that has sophomores for the probability that they're a sophomore, and then you have to add up the males, which would be the second row, which I already had the total up there earlier for that. And then your sophomores that are males, those are going to be 256 out of 2,149. Again, most likely you would look down and see percentages, and that is 61.8%. So this is the first day of the MCA practice, and you could see it's pretty high on probability and statistics. And what you're going to do for homework is go into Schoology. And scroll down. Where it says the black folder at the bottom, MCA Math Tutorial. This is your homework for March 26, 2021. And there is a video here made by Mrs. Gosha. And what it does is it shows you what to expect that you'll have to do on the MCAs as far as drag and drop or using multiple choice techniques, all of those types of things. So you need to watch this video, and that will be your homework. I just throw an extra credit problem on a test about part of this so that I'll know that you watched this. We have to get prepared for the MCAs, and this is going to be really good for you to see how the mechanics of getting the right answers works when we take this test completely online. So that's your homework for over spring break. Finish up any of those problems in the packet that we did not do together, and then watch this video, about 6 minutes long, I believe. Have a good spring break, everybody.